Hello, this video is about uncertainty and measurement. First, we'll talk about precision and accuracy. So accuracy is how close to the correct value that you have, and that's this row right here. And precision is about how close together your values are. So precise is this here. So this upper left-hand quadrant, these measurements are all close together and they are all on target. So this is both precise and accurate. This one here, they are all close together, but they've missed the mark. So this is precise, but inaccurate. This one in the upper right-hand side is accurate. These kind of all average to the middle, but they aren't very close together. They're very spread out. There's a lot of variation, so it's not very precise. These are spread out and not really centered. They're centered more over to the left than they are on the target. So therefore, these are both imprecise and inaccurate. Now we need to understand the difference between systematic error and random error. Systematic error is caused by flaws in equipment, in calibration, or in method. It's consistent and repeatable in one direction. In other words, there's a bias. And it affects the accuracy, but not necessarily the precision. Okay, so it affects the closeness to true value. So an example is a scale that always weighs 2 kilograms too heavy. If nobody's standing on it, it says 2 kilograms. If somebody that weighs 50 kilograms is standing on it, it will read 52 kilograms. So it's always 2 kilograms too heavy. That's a systematic error, and you can account for that. It also might be if you're missing if your meter stick is broken off at one end and you're missing the first 2 centimeters. Random error is caused by unpredictable variations given by like the environment, the limits, the observer, and so on. It varies in size and direction, and it affects the precision or the spread of results. So for example, your reaction time when you're using a stopwatch. If I ask you to measure a 4-second interval that you look at on an analog clock with the second hand going around, some people might start and stop in 4.1 seconds, some people 3.8 seconds, some people 4.5 seconds. So the variation from the correct answer is either 0.1 or 0.3 or 0.5. It varies and it depends on the person measuring, and it's unpredictable. It depends on reaction time. So that's random error, as different from systematic error. Least count of a measuring instrument is the smallest value it can accurately measure. If a ruler has millimeter markings, then its least count is 1 millimeter. Here's a picture of a scale. It looks like the scale is reading 200.2. It looks like the least count is 0.1, but really on this scale, it's 0.2, because what you can't see from the picture is that the scale can read 200.2 or 200.4 or 200.6, but it can never read 200.3 or 200.5. So in that case, the least count is 0.2 pounds. So when making a measurement, it's customary to write down all the numbers for the decimal places down to the least count or the most precise measurement on the tool, and then estimate for the last one. These are then the significant figures because they are precisely known except for the last digit, which is a good estimate. So here's an example. I've got these 2 pink bars here, 1, 2, they're the same length, and they've measured them up against 3 rulers, top, middle, and bottom. In the top ruler, the least count is 10 or 0 or maybe 20 way off the end over here. But if I look right around here, let me get a pencil. I can draw on here now, right around there. I would say that's roughly, well, I can tell down here it's 7, but if I didn't have that, I'd say this is about halfway. Not quite. Maybe this is halfway. So we'll just say that's 7. Okay. And so then if I look down at this ruler, I know that it's 7 point something, it looks to me like it's slightly less than half in this region here. So I might go here. Here's my pencil again. Give me the pen. There we go. 7.4, less than half. I can't say 7.41 or 7.45 or even worse, 7.4589. I can estimate that it's at about the 0.4 because it's less than half, okay? And then for the next one, down here, here's the 0.5. And so it's not quite 0.5, so we'll go with 7.4. And it's really not very far between 7.4 and 7.5 in here. So I think what I would call this one is 7.41. So for this ruler, which has millimeter markings, I can say 7 centimeters, 0.41. For this one that only has centimeter markings, I have to go with 7.4. And notice I'm estimating that last digit in each case. And this one that only has decimeter markings, I have to just say 7-ish centimeters, and that's an estimate. So that's how your tools that you're using give you your number of significant digits. So the rules for reading graduated cylinders are slightly different. You have a graduated cylinder here in milliliters. You can see this area is zoomed in over here. And so I can tell from the large picture, 5, 10, 15, 20. And then this is, so each one of these tick marks, 20, 21, 22, 23, 24, and 25. Each one of these is 1 milliliter. So there's 20. It's somewhere between 21 and 22. But where do you pick? You've got the edge up here, and you've got the edge up here, and then you've got the lower part. When you read a graduated cylinder, remember probably from chemistry and bio, you read the bottom of this meniscus. So for this one, I would say probably it's a little bit more than half of the way between the 21 and the 22. So you would say 21 point, so it's 20 and 21 point, I might say 21.6. You could even make an argument that that's 21.7, but you definitely wouldn't write 21 or 22. You would definitely estimate in between these two. This is more than half. Is it 0.6 or 0.7? I don't know. This is an estimate, but you always include the estimate when you record the numbers. So that's the end of our video on measurement and uncertainty. I hope that was helpful. I will see you in class.